topic in today's class. As I mentioned before, I'm going to cover only 7 slides, and we are going to about the Zener diode. Now, in order to cover the Zener diode, it is important that we're going to review briefly the actual diode. So, diodes are usually called, junction diodes. So, why do we call them a junction diode? Any ideas why a junction diode? Or also some people call them like a PN junction. Remember that?
Because of PNN type material it's made of.
Yeah, it's a P and an M-type material. So in the case of the Zener diode, it's going to be the same thing. The difference is that in the case of the junction diode, which is right here, okay, you have a positive and a negative. And the Zener is the same thing. You have a positive and a negative. But if we want to operate the junction diode, for the junction diode to be operated as a closed switch, it uses a voltage drop equal to 0.7 volts, roughly about 0.7 volts. And they are operated forward biased. Okay? And if you connect the junction diode reverse biased, then the diode is going to behave as an open switch. So this is forward biased, and it's going to behave as an open switch when it's reversed biased. Okay, and that's why we can use it for rectification, because by doing that, we are going to be able to filter the negative signal, okay? And the signal, only the positive signal is going to go through the diode while the diode is being forward biased, or in other words, while the diode is turned on. Now, when it comes to the Zener diode, on the other hand, is just a regular diode, but instead of working forward bias, it's going to work when it's reverse biased. And that's what we are going to be getting into this morning, okay? So also we are going to be discussing common applications of the Zener diode. And also I'm going to do a simulation of the Zener diode in a circuit. If you have this book, do you have the industrial motor control? Can you see what I'm holding in my hand now?
Yeah, somewhere.
Oh, you see it somewhere. Oh, somewhat. Okay, yeah, because it's rather small. Like in unit, it is in unit, like in my book, because I have the older version. Okay, in unit 58, that's what I have the Zener diode. So there's a small circuit that I'm going to show you anyways on the PowerPoint, where we are going to simulate what happens with the Zener diode and how is it that the Zener diode has the ability to maintain a constant voltage through the load. Okay. So now, the Zener diode, as we can read on the slide, it is a device that's designed to be operated with reverse polarity. Now, when any diode is broken down into its reverse direction, like in the case of junction diodes, the junction diode will actually break down when it enters its Zener region. In other words, okay, I'm gonna be putting this here again. If we have a regular diode, let's say that this diode have a peak voltage, okay? Let's say that it have a peak inverse voltage of 50 volts. Now, this nowhere, I don't know if you are familiar with the term peak inverse voltage. That is the maximum voltage that the diode is going to be able to pretty much like hold, behaving as an open switch. And once you go above that peak inverse voltage, the diode is going to break down. That's in the case of junction diodes. Any questions about that? When the diode is connected positive to positive, okay, so if the power source is here, and it's connected like positive to positive, and here, let's say we have whatever, a load. In this instance, the diode is going to behave, as I said before, as a closed switch, right? Now, something important here. If we connect this diode backwards, okay, so let me do this. Okay, let's say that, okay, this doesn't want to delete there. If I connect it backwards in such a way that I have my negative signal, okay, like here. Let's say like if I have my negative signal here and my positive here, then this diode is going to be behaving as an open switch. And because it's behaving as an open switch, if we exceed their peak inverse voltage rating, then the diode is going to break down. Okay, so now in the case of the Zener diode is designed to work in reverse direction. And we are going to see why in just a minute. Okay. 1 second. Oh. Okay, so hello guys. Any questions? Is everyone still here?
Oh yeah.
So let's go through this slide here. Okay. So in here, like in this case, we see the following. This is a regular diode here. A regular diode is going to be using our 0.7 volts, and once it has 0.7 volts, it's going to conduct current. So this horizontal line represents voltage, and this vertical line represents the current in the diode. Once you get to the 0.7 volts, as you can see here, then it's going to be conducting current without any problem, okay? Of course, it's always fed to the current rating of the diode itself. When the regular junction diode is, I mean, like when it's behaving as an open switch, because it have a reverse voltage, once that reverse voltage is exceeded, it's going to break down, and it's just going to break down completely, and it's just going to be completely open. Okay, so it's not going to allow the flow of anything at all. It's just going to short pretty much. Okay, So two things could happen. You know, it could either break down and block completely the flow of current, or it could short out and just have an avalanche of current going through it, and it just behave as a dead short, or as a complete closed circuit, because it doesn't have the ability to continue to block the inverse voltage. Like in the case of the Zener diode, when the Zener diode reaches this region where it goes to its max reverse voltage, then the diode starts to conduct current. And once the diode starts to conduct the current, it's going to allow any increase in current. It's not, number one, it's not going to burn out the diode, and it's going to cause that anything which is connected in parallel with that diode to have the same amount of voltage drop that the diode has. So something important here to keep in mind is that Zener diodes are always connected in parallel with the load. Why? Because what happened with in parallel circuits? I mean, what
voltage drop is the same?
Yeah, voltage drop is the same. So if the Zener diode behave in this manner, and it will always have, let's say, like in the example that we are going to see, we are going to have a Zener diode that have a voltage rating of 12 volts. So when it reaches the 12 volts, it's going to allow a huge amount of current to flow through it, and anything which is connected in parallel with the diode will have 12 volts constant, or the constant 12 volts, because I mean the rule is, it is a rule that in parallel always voltage stays the same. And I mean there's nothing that we can do to break that rule. I mean that's pretty much the law that we are going to be into, you know, that we are going to be navigating in. Any questions about that? Okay, so we are good so far. Okay, so this is what I already mentioned, that the voltage drop of a Zener diode is constant, and any device connected in parallel to the Zener diode, we have a constant voltage drop, even if the current through the load is changing, okay? And also we are gonna be able to do the calculations using Ohm's law and see how everything holds together. So here we have the symbol for a Zener diode, and it's important to keep in mind that they are connected in reverse polarity. So this is the same circuit that I recreated on multisim. So here we have R1, and R1 here is going to be the current limiting resistor for the whole circuit. In this instance, I have a 12 volt rated Zener diode. Please notice that the Zener diode is connected, reverse bias is connected in reverse polarity. And we have the voltage, the input voltage of the source has to be greater than the Zener voltage of the Zener diode. Okay, so in this instance, we have an ammeter here that we are going to call A1, because we want to be able to observe how much is going to be the current through the Zener diode and how much is going to be the current through our load. In this case, we have a 200 ohm resistor, which is connected in series with a variable resistor that has a value of 1 kilo ohm. And then we had a voltmeter, which is connected in parallel with the whole circuit in order to see if the voltage through the load is going to remain constant. And even when we change the current, here, and the way that we are going to be able to change current in here is by changing the value of the variable resistor. Even when we change this current, this voltage through here is going to remain the same. It's not going to change at all. Okay. Any questions about that? Or you want to jump into the simulation and see how it actually works?
Let's see how it works.
So let's get there then. Let's get there. So this is the same circuit that I was telling you about. Okay, let's do the following. Like if we were to calculate, like we have a 20-volt power source, we had 100 ohms, excuse me, resistor, which is the current limiting resistor, and then we got our Zener diode. The Zener diode, the actual Zener diode, it is rated for 12 volts. So we would be able to calculate, you can see it here, that we have 12 volts at this point in time. Okay, we can see that we have 12 volts drop through this load. And now we are going to, because we connected the Zener diode in parallel with the load, we are going to be able to keep that voltage constant regardless of how much resistance I decide to use right here on my load. The only thing that you are going to be able to see that changes is going to be this, my current. Now, let's do a little bit of Ohm's law here, okay, before we move ahead. If we were going to use Ohm's law, of course, we can see that we had a voltage drop here of 12 volts. We can see that on the voltmeter. So that we would be able to determine at this point in time how much voltage we have right here on that resistor. So what would be the voltage of that resistor?
8 volts.
8 volts, perfect. Now, if we use Ohm's law again, and we say, well, I have, and I'm just gonna put it right there, just 1 second. So if we say the following and we say, well, I want to determine my current I1, it is equal to my 8 volts divided by 100 ohms. That is equal to how much?
.08.
Pardon me? 0.08.
.08.
Perfect, which is exactly what we have in there. Measure through the ammeter. In other words, that would be equal to 80 milliamps. Okay, so can you see in here, can you still see in here that, well, so through the actual Zener diode, we have 20 milliamps, while through this load, we have 60 milliamps. If we were going to use Ohm's law once more, and we say, well, we have 200 ohms in here. So let's see if Ohm's law is holding together, okay? So let's calculate to see if that 60 milliamp current is right. So that way we are going to be able to observe that I am not tricking you, right? So in this instance, we have our 12 volts divided by my 200 ohms, okay? So please keep in mind that here, even when this one says 1 kilo ohm, this is a variable resistor. And right now, the value of that variable resistor is 0%. So I have a small slide button that I'm going to be able to use right at the bottom there in order to change the value of my 1 kilo ohm resistor. Now, when we do our 12 volts, let's get back to this. When we do our 12 volts divided by 200,
You come out with 60 milliamps.
Perfect. So it's going to give us like 0.06 amps, which is 60 milliamps. And we can see that still the rule for parallel circuits, that the total current is going to be equal to I1 plus I2. Still, that rule is being maintained. Okay, so we are not violating any rules. Everything, I mean, always has to match. Any questions about those calculations?
Nope, sounds good.
Sounds good. Okay, perfect. So let's do the following. So what's going to happen now? I'm going to get rid of this. What's going to happen when I decide to increase the value of my load from 200 ohms? I increase it to 400 ohms. I want you please to see what happened right there. Can you see what happened? As I increase my value, still the voltage remains the same. Still is going to be 12 volts. Okay, so still the total current through the circuit still is going to be my 80 milliamps, but now the Zener diode is taking the excess current. Okay, so now, like, even when I was able to increase my, or even when I was able to change the current through my load, still the voltage, the full voltage remains the same, because the excess current is going to be taken by the Zener diode. Even if I continue to increase my current, my resistance through the load, you can see it right there live what's happening. As I continue to increase my resistance, because of Ohm's law, if I increase resistance, current is going to be reduced through my load. However, voltage continue to remain practically the same, because the excess current, okay, is going to go through the Zener diode. And at the end of the day, the total current was able to remain being the same. Now, one of the applications that the Zener diodes are used for is to be used with changing with different input voltages. Let's say, like, if you have a fluctuation in voltage, because whatever, like you have a surge, or you have fluctuation, in your input voltage, you are going to be able to protect sensitive equipment from having changing voltages with the Zener diode, because Zener will continue to supply the same voltage to any component that is connected in parallel with it. I'm going to simulate that for you, okay? So let's increase this voltage from 20 to 25 volts, and let's see what happens, okay? So please keep in mind that by increasing the voltage, I should be able to increase my current. It's Ohm's law, right? If voltage goes up, then our current is supposed to go up. So when that happens, okay, so now we can see that still, yes, the current went up to 120 milliamps because voltage went up, but still we continue to have our 12 volts right at the load. And that's what I want you to be able to see. And it doesn't really matter if I change the current through my load, I will still continue to have my 12 volts through the load. If I increase the voltage even a little bit more to 30 volts now, I will increase my current, my total current, to 179 milliamps, but I still have pretty much 12 volts. We could say, well, if 12.1 is like 97 millivolts extra that I have there, but it's not a huge increase, okay? And that's pretty much the use of the Zener diode. Even if I were able to change this voltage here, I will be able to keep the same amount of voltage through my load. If I have a voltage reduction from 30 volts, let's say to 15 volts instead. Okay. So that one, okay, affected the Zener diode. And my voltage was dropped to 10 volts. But as I increase my voltage to the value where it should be, you know, once it reaches that peak inverted voltage, that is going to have that is going to cause my diode to have a voltage which is equal to 12 volts. Then, of course, I'm going to be able to, in that instance, to keep a constant voltage through the load. Like if I wanted to play, let's say if I wanted to reduce the voltage because I want to use a reduced voltage, I could make this resistor 50. Okay, let me go back to the 15 volts. I could make it like 50 ohms. And by doing that, I'm going to be able to have, well, that was too much current for my Zener. Oh, no, it wasn't. Okay, so I'm going to be able to, by reducing this resistor, I'm going to be able to have less voltage drop on this resistor, thus allowing the Zener diode to reach its rated inverse voltage. Okay, so any questions about this simulation?
Oh, all good.
All good?